All right, having said that, let's now introduce Hee Oh, who's a professor of mathematics at Yale. I learned about Hee's work at the UCLA conference in 1999 or 2000 from Peter, so this is coming full circle. For me, it's lovely to be in this position. And the title, anyway, the title of Hee's talk is Rigidity of Kleinian Groups and Zariski Density in Higher Rank.
Thank you.
I will make that announcement at the end.
Right, restaurants are more important than my talk. So so I'll talk about rigidity of Kleinian groups, and I got into actually this topic of Kleinian groups 100% thanks to Peter. So I'm very pleased to and happy to give this talk for this special occasion for Peter. So many of the talks were about number theory, and there is no number theory here, but there will be a lot of pictures. So what is a Kleinian group? So Kleinian group is a discrete subgroup of PSL2C. Okay? So the rigidity question is this. So given a discrete faithful representation, gamma of PSL2C, discrete simply means that the image of the representation is a discrete group, and faithful means it's injective. Okay? So given a discrete faithful representation, say rho of gamma into PSL2C, when does this representation rho extends to a Lie group isomorphism from PSL2C to PSL2C? Okay? So of course, if you have a Lie group isomorphism from PSL2C to PSL2C, then you can restrict your representation to gamma, and then that will give you discrete faithful representation. So we call these representations trivial representations because they exist for trivial reasons. Okay? So please don't get confused. The trivial representation does not mean that everything goes to identity in my talk. Trivial representation simply means that representations which exist for algebraic reasons. So they are the restrictions of representations of ambient Lie group. So this question is related to the rigidity of hyperbolic three manifolds. And understanding this context will be important for my talk. So I'll give you some basic information. So I'll consider the apart space model of H3. Okay? So we have this x1, x2 plane, and then apart space model is simply above the x1, x2 plane. So H3 consists of these triples x1, x2, y, and y is a positive number. And hyperbolic metric is simply the Euclidean metric over the last coordinate, y. So in this model, it's clear what is a geometric boundary. I have x1, x2 plane for point at infinity. And I can identify also x1, x2 plane with a complex plane. So here the geometric boundary is extended complex plane, and topologically it's a sphere. So in this model, in this apart space model, geodesics in hyperbolic 3 space are either vertical lines or the circles intersecting this geometric boundary orthogonally. Now, what is isometry group of H3? Poincare extension theorem says that the group of Möbius transformations of the extended complex plane is precisely the group of isometries of H3. So Möbius transformation, by definition, it is a composition of finitely many inversions with respect to circles. Okay? So what is an inversion with respect to circle? So it's illustrated in this picture. So if I have a circle of radius r with center A, then inversion with respect to circle maps here P to P prime, where P prime is the unique point line in the line connecting the center A and point P, and P prime must satisfy this equation. The distance from P to A times the distance from P prime to A should be exactly the radius square. So this is the definition of inversion with respect to a circle. Okay? So now to understand the Poincare extension theorem, we have to understand how to think of inversion with respect to circle as an isometry of H3. So how does this act on H3, first of all? And it's illustrated in the second picture. Okay? So given a circle, so we'll consider the northern hemisphere, and then we'll consider inversion with respect to this northern hemisphere. Okay? So now inversion with respect to this sphere is defined exactly in the same way. So P will be mapped to P prime, and then P prime must satisfy this equation. Okay? So it is clear, if I have a point above the x1, x2 plane, the image of this point under the inversion with respect to this northern hemisphere will lie on the apart space. Right? So it preserves the apart space, and moreover, we can check that the inversion with respect to this northern hemisphere will preserve the hyperbolic metric. So it gives us the isometry of H3. And this Poincare extension theorem says that every isometry of H3 arises in this way. It will be a composition with respect to inversions with respect to these orthogonal spheres to the boundary. Okay. So now the group PSL2C acts on extended complex plane by linear fractional transformation. So it maps A, B, C, D, maps Z to AZ plus B over CZ plus D. So it's a linear fractional transformation. And via this action, we can write every element of PSL2C as a composition of an even number of inversions with respect to circles. So that means PSL2C is precisely the group of orientation preserving isometries of H3, which is the index 2 subgroup of isometry of H3, which is same as the group of Möbius transformations of the complex plane. So now, Kleinian group is a discrete subgroup of PSL2C, and we just identified the PSL2C with the group of orientation preserving isometries of H3. So for given Kleinian group, so it acts on H3 as isometries and preserving orientations, and it also acts properly discontinuously because it's a discrete subgroup. Okay? So that means we can form a quotient manifold. So H3 quotient by gamma will give us hyperbolic 3 manifold, and conversely, any complete oriented hyperbolic 3 manifold can always be presented in that way, H3 by some Kleinian group. And this Kleinian group gamma is precisely the fundamental group of the hyperbolic 3 manifold. And this is the reason, actually, why the Kleinian groups play a very important role in the study of hyperbolic 3 manifolds. So we'll be interested in the following classes of Kleinian groups. So first, lattices, and geometrically finite groups, and finitely generated groups. So a Kleinian group is called a lattice inside the PSL2C if the corresponding hyperbolic 3 manifold has finite volume. Okay? So you have this quotient manifold. If it has finite volume, we call such a Kleinian group lattice. So it's not obvious, actually, why lattices should exist. Okay? But they exist, and maybe I do say the word number theory. Many of the constructions are actually due to number theory. But it is actually not very easy to actually construct lattices. Okay? Now, Kleinian group is called geometrically finite if gamma admits a finite-sided fundamental domain. So, or actually geometrically, so you should imagine this picture. The corresponding hyperbolic 3 manifold, all the topologies actually is captured in the compact part, possibly with some cusps. Okay? And then it's easy to understand actually how the manifold actually goes to infinity. So this is what geometrically finite hyperbolic 3 manifolds are. And it's much easier to construct geometrically finite hyperbolic 3 manifolds. And so this class is much larger than lattices. And all geometrically finite groups are finite generated groups. So let gamma be any Kleinian group, and then we consider discrete faithful representation of gamma into PSL2C. So we'll be collecting all discrete faithful representations of given Kleinian group gamma, and then I'll denote that by R disk gamma. Okay? So R disk gamma is the collection of all discrete faithful representations of gamma, and it is called the discrete locus of a representation variety. So now, if I have a Möbius transformation G, and then we can consider the conjugation map. So we map gamma to G gamma G inverse. Okay? Because PSL2C is a normal subgroup of the group of Möbius transformations, the image will lie inside the PSL2C. So we get a discrete faithful representation. And these are exactly trivial representations. So in other words, actually, because the Möbius transformations are precisely isometries of H3, it means actually corresponding hyperbolic 3 manifold, the H3 mod gamma, H3 mod rho gamma, they are isometry. So clearly, the trivial representations are contained in this discrete locus of the representation variety. So the rigidity question is about find some weak hypothesis on this representation which implies that the representation has to be trivial. So what condition can you impose on the representation which would force it to be trivial representation? And here is a celebrated theorem of Mostow about 50 years ago. So Mostow rigidity theorem says that if gamma is a lattice inside the PSL2C, So meaning that a corresponding hyperbolic 3 manifold has finite volume, then any discrete phase representation is trivial. So it's just conjugation by Möbius transformations. In other words, the whole discrete locus just consists of trivial representations. You don't see any other interesting representations. So indeed, actually, Mostow proved this theorem only for cocompact lattice, meaning that the quotient manifold is compact. And the non-compact finite volume case was proved by Prasad, extending Mostow's approach. Yes?
Can you remind me of definition of R?
This is the collection of all discrete phase representations of gamma into PSL2C. Okay? So we are interested in discrete representations. So it's a collection of all of them. Okay? So even though I stated this theorem only for dimension 3, the same statement is true for any dimension, but higher than 3. And it is false for dimension 2. So just like we identified the PSL2C with the orientation preserving isometries of H3, the hyperbolic 3 space, PSL2R can be identified with orientation preserving isometries of hyperbolic plane H2. And if gamma is a lattice, then when you consider the corresponding hyperbolic surface, H2 mod gamma, so this is a finite area Riemann surface of finite genus. G is finite and also finite number of punctures P. Okay. So here's my picture. So here I have genus 2 and then I have 3 punctures. Okay. So in this case, the whole discrete locus of gamma divided by conjugations, modular conjugations, this is precisely what is called the Teichmann space of the surface S. And it's known to have these huge dimensions. So it's diffeomorphic to R to the 6G minus 6 plus 2P. So it's very, very far from being trivial. So Mostow theorem, completely settles our rigidity question. So now, what about for general Kleinian group? What about for non-lattices? So in studying general Kleinian group, what is called the limit set plays a fundamental role, and then here's the definition of the limit set. So gamma is a fixed Kleinian group. So to define the limit set, we consider this a pop space model again, and then take any base point O, and then look at the gamma orbit. Okay? So I have countably many points. And then because gamma is discrete, there is no accumulation point on H3, but then they will have accumulation on the boundary, and that is the limit set. However, it is actually best explained by this snow falling picture. So here I have a snow falling, and sorry that my snows are blue, it's not white. So you have snow, you have this snow falling down, and then wherever it accumulates on the land, on the ground, that's exactly my accumulation points, and then this is the limit set of gamma. Okay? And my ordinary set, by definition, it will be a complement of the limit set on C hat. Okay, so if gamma is a lattice, so what is a lattice? Lattice means that the quotient manifold has finite volume. It means that lattice is a huge discrete group. I mean, so H3, you see this is huge, and then for the quotient to be finite volume, gamma has to be huge group. Then means that actually the snows are falling everywhere, and then the whole Earth is covered by snow, so the limit set is everything for lattices. Okay? So for lattices, so this notion of limit set is not interesting. However, for non-lattices, this is very interesting and important object. And here are some images of the limit set. So these images are due to McMullen and Zhang. So here actually, so in the first picture, by the way, so the black part is the limit set and the white part is the ordinary set. In the first picture, it may not be obvious, but this is homeomorphic to a circle. The limit set is homeomorphic to a circle. Okay? So you have two components. And then in the second picture, so the limit set, you have here, you look at these round open disks, and then the limit set is a complement of these countably infinitely many round open disks. Okay? And this is known to be homeomorphic to a Sierpinski carpet. And in the third picture, this is similar, but now disks are not round. These are just topological disks. Okay? And in the last picture, this is called the Schottky dust. So this is now totally disconnected limit set. Okay? So it's important to have these images in mind, actually, for the rest of the lecture. So I wanted to show you this picture. So Alphonse measure conjecture says there are two kinds of limit sets for finite generated groups. So for any finite generated Kleinian group gamma, either limit set is everything or its Lebesgue measure is equal to 0. So limit set is a subset in the extended complex plane, so we can talk about Lebesgue measure of this set, right? So the theorem says that either it's everything, not only the full measure, but it's everything, or the Lebesgue measure has to be equal to 0. So this was observed earlier by Thurston and Canary. So this would be followed from what is called the Thames conjecture. And the Thames conjecture is proved by Igor and Kalagari-Gabay. So now this is theorem. Alphonse himself proved this conjecture for gamma geometrically finite. And in that case, the first case, lambda is everything happens only for lattices. Okay? So Alphonse theorem, Alphose's proof for gamma geometry finite says that either gamma is a lattice and therefore limit set is everything, or the Lebesgue measure is equal to 0. However, there are finite generated geometrical infinite groups, so therefore non-lattices whose limit set is everything. For instance, a theorem of Igor implies that every lattice contains such a subgroup. So you do have a lot of interesting geometrical infinite groups with full limit set. So now, when the limit set is everything, so Sullivan proved what is called the quasi-conformal rigidity. Okay? So let me explain what is this quasi-conformal rigidity is. So if you have two domains, D and D prime, an orientation preserving homeomorphism, say F from D to D prime, is called the K quasi-conformal. If it maps infinitesimal circles, very, very small circles, to ellipses of bounded eccentricity bounded by K. Okay? So there's a formal definition here, but maybe the picture can be more helpful. It says that if I have a very, very small circle, then the image has to be contained in an annulus whose modulus is bounded by K. So that's what K quasi-conformal means. So if F maps actually all the infinitesimal circles to infinitesimal circles, in that case, F is a one quasi-conformal, and it's not obvious, but it's a theorem. One quasi-conformal means F has to be conformal, meaning that F is holomorphic with a non-zero derivative. Okay? So therefore, if F is a one quasi-conformal on the whole Riemann sphere, then F is a conformal automorphism of C hat, so therefore it is a Möbius transformation. And then we know that the Möbius transformations are characterized by property. It maps circles to circles. Okay, so these three statements are equivalent. So now representation, gamma into PSL2C is called the quasi-conformal deformation if there exists an equivariant quasi-conformal homeomorphism of the Riemann sphere. In other words, it simply means that my representation rho is given by a conjugation by a quasi-conformal homeomorphism. Okay? So for every gamma, in gamma, rho gamma is simply the conjugation by some quasi-conformal homeomorphism, F composed by gamma composed by F inverse. So remember, if I have a trivial representation means that it is a conjugation by conformal automorphism because Möbius transformations are exactly the conformal automorphisms. So the trivial representation are quasi-conformal deformations. Of course, however, it is not clear if there is any other non-trivial quasi-conformal deformations. Nevertheless, we collect all quasi-conformal deformations, and that is called the Tychonoid space of gamma. Okay? And clearly, quasi-conformal deformations are contained in the discrete phaseful representations. So we have this picture. So I have a collection of all discrete phaseful representations, and inside I have this Tychonoid space of gamma, which is the quasi-conformal deformations of gamma, and then of course it contains trivial representations. So these quasi-conformal deformations played an important role already in the proof of Mostow. So Mostow's rigidity proof for cocompact lattice. So Mostow's proof consists of two steps. So the first step is this. So if I have a cocompact lattice, it means I have a compact fundamental domain in H3. And then by translating this compact fundamental domain by elements of gamma, I get the tessellation of H3 by compact fundamental domains. Okay? And then using this representation rho, so Mostow gets a map from H3 to H3, which is almost isometry. The error will be just this compact fundamental domain. So that is called quasi-isometry. So he first obtains equivariant quasi-isometry from H3 to H3, and then he goes to infinity, meaning that to the boundary. And he shows that this quasi-isometry can be extended to a quasi-conformal homeomorphism on the boundary. And then the second step is that there is no quasi-conformal equivariant homeomorphism on the boundary, so meaning that type-conformal space of gamma is trivial. Okay? So the second step, he uses the ergodicity of the geodesic flow on finite volume hyperbolic manifolds. So second step involves the dynamics of Kleinian groups. And Sullivan's quasi-conformal rigidity theorem says that the step 2 is always true as long as limit set is everything. You don't have to have a lattice, but as long as limit set is everything, the second step of Mostow's proof is true. So here, gamma is any finite generated Kleinian group with full limit set. Then any quasi-conformal deformation is just a conjugation by Möbius transformation. So the type-conformal space of gamma just consists of trivial representations. So this is Sullivan's rigidity theorem. So in fact, actually, Sullivan proved a theorem which is seemingly more general than this statement. What he proved is that if you have a quasi-conformal homeomorphism, and if it's conformal on the ordinary set, omega, so remember, ordinary set is the complement of the limit set. If it's conformal on the ordinary set, then this F has to be a Möbius transformation, and hence the representation has to be trivial. Okay? So if the limit set is everything, then what is the ordinary set? If the limit set is everything, ordinary set is empty set. Right. So therefore, this conformal on omega, this condition disappears. So this statement is more general than the statement of Sullivan's rigidity theorem. On the other hand, Alphonse measure conjecture says that if omega is non-empty, then omega has a full Lebesgue measure on the plane. And then if you have a conformal map on a full Lebesgue measure set, then measure of Riemann mapping theorem says that it has to be conformal. So therefore, Sullivan theorem has meaning only when limit set is everything. Okay? But it is also true at the same time, if the limit set is not everything, then his theorem is not supposed to be true. So if the limit set is not everything, type-conformal space of gamma is in fact huge. So by something called Alphonse finiteness theorem, so gamma x on the limit set, it preserves the limit set, so therefore it preserves also the ordinary set, and then its action is properly discontinuous. So we can form a quotient of the ordinary set by gamma. And the Alphonse finiteness theorem says that this quotient is a Riemann surface of finite type. Okay? And if we denote by S1 to Sk, these connected components, then the type-conformal space of gamma is essentially same as the product of type-conformal spaces of these Riemann surfaces, which we have seen highly non-trivial. Okay? So if omega is non-empty, then the type-conformal space of gamma is huge. So now we have to ask, so if lambda is not everything, then what should be our rigidity questions? Okay? So what conditions on rho would guarantee rho is trivial, or the corresponding quasi-conformal homeomorphism is a Möbius transformation? So what Sullivan proved is that if F, this quasi-conformal homeomorphism, is conformal on the ordinary set, then F has to be a Möbius transformation. So we take actually hint from the Sullivan theorem, and then we wanted to ask, what if F is conformal on the limit set? Okay. So, but okay, limit set here, in our case, it has a Lebesgue measure 0. So what do I mean by conformal on a Lebesgue measure 0 set? So we proposed this to be understood in the sense that F maps all the circles in limit set to circles. And by circles in the limit set, I simply mean circle intersection limit set. Okay? Suppose I have a quasi-conformal homeomorphism which maps all the circular slices of the limit set to circles. Is it true F is a Möbius transformation? Okay? So this was the question. So I proved this theorem with Dong-Yul Kim, who is my current graduate student, 2022. So statement is this. So let rho be a quasi-conformal deformation and let F be an associated quasi-conformal homeomorphism. And here we have to assume my Kleinian group gamma and then its image rho gamma, they are both Zariski dense in PSL2C. Okay? Otherwise, the statement is not true. So now I need to be careful. What do I mean by Zariski dense inside PSL2C? So here we think of PSL2C as a 6-dimensional real algebraic group. Okay? So that's what you mean by Zariski dense over here. So, or you can think of PSL2C as the orthogonal group of signature 3,1. So for instance, PSL2R is not Zariski dense, okay? When you think of PSL2C as a real algebraic group. So now our theorem states, so the condition is that suppose our ordinary set has at least 2 connected components. This is the hypothesis. Okay, so of course this is same to say that the ordinary set is not connected, right? But we wanted our theorem to sound positive instead of negative, so we formulated our conditions that it has 2 connected components instead of saying it is not connected. Okay? So here is actually a picture. So this condition is satisfied, of course, in many situations. Like I showed you this picture. Here the limit set is topologically circle. It has 2 connected components. So it's satisfied by this. And then here, of course, there are infinitely many connected components. So what I like about this hypothesis is that you can see whether this condition is satisfied or not. It's very easy to check. Now the theorem is that if F is conformal on the limit set, in the sense that F maps circles in the limit set to circles, then in fact F is a Möbius transformation, and the corresponding representation is just conjugation by this Möbius transformation. So this is the theorem. Okay, and I want to emphasize we are not asking F would map the whole circle to circle. Okay? But for instance, here's the illustration. So here I consider this circle here. This circle intersects the limit set at 4 points, right? By the way, so if the circle intersects the limit set less than 3 points, then this condition is meaningless because every 3 point lies in a circle. Okay? So in this example, I drew this circle which contains 4 limit points, and then I'm not asking this pink circle to be mapped to a circle. I'm only asking the 4 points here goes to 4 points which lies in some circle. Okay, so this is the hypothesis. Any question about the statement?
Is the first hypothesis necessary? Like, are there counterexamples if you get rid of it? First hypothesis?
So the first case, actually, this hypothesis is not satisfied. This shocky dust. When you have this totally disconnected set, the shocky dust, in that case, gamma is a free group. So probably you have lots of representations, but also that brings actually interesting question that is there an example of a shocky group that every circular slice has less than 3 points, and most 3 points. So I've asked the people around, and then I don't think there's such an example yet. But so in fact, we prove our theorem in a slightly more general condition. There is some precise hypothesis on the limit set, but then but this condition is easier to state. Okay? So in fact, actually, so we prove our theorem for general discrete faithful representation, not only for quasi-conformal deformation. And for that, I need to introduce this notion of a boundary map. So a row boundary map is a row equivariant continuous embedding of the limit set to the boundary. So this is the definition. So for given discrete faithful representation, so I said when studying rigidity, you have to go to infinity. Okay? So you have to go to infinity. So this is the mantra started by Mostow. You go to infinity. And for general Kleinian group, my infinity is the limit set. Okay? So I need some condition on the limit set. So in general, the boundary map does not have to exist, but if it exists, there can be at most 1. So what is the idea about the limit set? So here, suppose I have my limit point cushy. Okay? By definition, cushy is a limit point means that cushy is the accumulation of some sequence gamma IO here. Okay? And I want this cushy to be mapped to F cushy, which should be an accumulation point of the corresponding sequence by the representation, rho gamma IO. So this might not be well defined, but if this is well defined, then the boundary map has to have this property. Okay? So there can be at most one. But there are many situations this boundary map exists. For instance, these quasi-conformal deformations. So we simply restrict our associated quasi-conformal homeomorphism to the limit set. So that is our boundary map. So quasi-conformal deformations come with the raw boundary map. And another very important situation that this boundary map exists is the case when both gamma and the rho gamma are geometrically finite. Okay? And also type preserving. So type preserving means that it maps parabolic points to parabolic elements and then loxodromic elements to loxodromic elements. Maybe for this audience, instead of parabolic elements, I might want to say unipotent elements. It maps unipotent elements to unipotent and then diagonalizable elements to diagonalizable elements. Then the representation is called the type preserving. And in that case, the row boundary map always exists. So this is a two-case theorem. So hypothesis on the existence of row boundary map, this is satisfied in a very general situation. So now here's our theorem. So again, we assume gamma and rho gamma are both Zariski dense. But then now we are not assuming rho is a quasi-conformal deformation, but any discrete faithful representation. And as before, we assume the ordinary set has at least two connected components. And now instead of asking this boundary map is conformal on all of lambda, we can actually weaken the hypothesis. So F is now only locally conformal on lambda in the sense that F maps some open collection of circular slices of lambda to circles. Okay? Then, as before, rho is trivial, and moreover, this boundary map, in fact, has to extend the whole boundary as a Möbius transformation. Any question about the statement? Okay, so this answers actually some question asked by Kurt McMullen, and to explain that, so I want to note that. So if you have 4 points on the boundary, so here actually I drew a hyperbolic ball model instead of a pop space model here. So if you have 4 points on the boundary, then it determines unique ideal tetrahedron in H3. Okay, so here I have 4 points here, and then it gives me this ideal tetrahedron in H3. And then here I have 4 points, it gives me this unique ideal tetrahedron associated to it. Okay? So by now, actually, there are several different proofs of Mostow-Rigidity theorem. And one proof actually given by Gromov and Thurston uses the following theorem. It says that if you have a homeomorphism from a sphere to sphere, and if this homeomorphism maps vertices of maximum volume tetrahedron to vertices of maximum volume tetrahedron, then F has to be a Möbius transformation. Okay? So this is a step used in Gromov-Thurston proof of Mostow-Rigidity theorem. Of course, we have a tetrahedron in H3. We can talk about volume, and then it is about maximum volume tetrahedron. So McMullen's question also about actually the other extreme case. So let me ask, what is the other extreme of maximum volume? Zero volume, right? The minimum volume, zero volume, exactly. So note that actually in this second picture here, these 4 points lies in a circle. And then tetrahedron determined by these 4 points has a zero volume in H3. Okay? So because of this, actually, our theorem is equivalent to, oh, sorry. So I forgot about these slides. Right, McMullen's question was exactly about this. Instead of F maps vertices of maximum volume tetrahedron to maximum volume tetrahedron, what if F maps vertices of zero volume tetrahedron to zero volume tetrahedron? What can you say? So because the zero volume tetrahedron are defined exactly by these 4 points lying on a circle, so our theorem is in fact equivalent to this formulation. So if my boundary map, which is a map on lambda to C hat, is a continuous embedding of the limit set, if it maps vertices of zero volume tetrahedron to vertices of zero volume tetrahedron, indeed F extends to a Möbius transformation, and then the corresponding representation is trivial. And I want to again emphasize our boundary map is only defined on the limit set. So here, when you say zero volume tetrahedron, we only mean those determined by 4 points on the limit set. Okay, so this is much smaller class. And here is another formulation in terms of cross-ratio rigidity. Indeed, actually, I gave a relay talk in Princeton about 1.5 years ago, and then Michael Eisenman was in the audience. And then when I talked about this, he asked me, what about cross ratios? And then at that time, I didn't remember actually this formula. So then actually, we added this in our paper after this lecture in Princeton. So if you have 4 distinct points, Z1, Z2, Z3, Z4, the complex number, then the cross ratio is defined by this ratio. So it's not important what the formula is, but what is important is that the cross ratio of 4 complex numbers is a real number if and only if these 4 points must lie in a circle. Okay? And then the proof is this, because you compute the cross ratio of infinity, 0, 1, Z, it is Z. Okay? So infinity, 0, 1, this lies on the real line. Okay? The real line is a circle in the extended complex plane. So Z lies in the same circle as infinity, 0, 1, Z is exactly the same as Z is a real number. So this is the proof of this statement. The cross ratio of 4 numbers is a real number if and only if these 4 complex numbers must lie in a circle. So then our theorem has this, again, equivalent formulation. So if our boundary map preserves realness of cross ratios, then F has to extend to a Möbius transformation. Okay? Again, let me emphasize, we are not asking F preserves the values of cross ratios, but we are only asking F preserves the realness of cross ratios, meaning that 4 points with a real cross ratio must be mapped to 4 points with a real cross ratio. Then F has to extend to a Möbius transformation. So this is the statement. So now I'll say a few words about how we prove this very beautiful theorem. So we go to the higher rank. So I have a Kleinian group, and then I have a discrete faithful representation. And we will look at this embedding of gamma as a graph in the product of 2 PSL2C. Okay? So I have a PSL2C times PSL2C, and then my group, which we call our group, which we call self-joining, is of the form. It consists of the elements, the pairs gamma, comma, rho gamma. So you can think you embed the gamma diagonally into PSL2C times PSL2C, but the second component you have to twist by the representation. Okay? Now the product of PSL2C and PSL2C, this is now isometry of the Riemannian product of 2H3. So isometry of H3 times H3. Now this is a rank 2 symmetric space. Okay? So rank 2 symmetric space. So my group is now higher rank, in higher rank. And again, here's a cartoon picture. So because gamma rho is a discrete subgroup of isometry of this Riemannian product of 2 H3s, we can form a quotient. I get this locally symmetric manifold, H3 times H3 mod my self-joining group gamma rho. And then it projects to my first hyperbolic 3 manifold, H3 over gamma, and then it projects to my second hyperbolic manifold, H3 over rho gamma. Okay? But it's sitting above over there. So very simple but fundamental observation is this. My representation rho is trivial can be detected by the Zariski density of this self-joining group inside the PSL2C times PSL2C. So if my representation is rho is trivial, that means rho is simply conjugation by a Möbius transformation, right? So it means that I have some G such that the group look like a gamma, and then G gamma G inverse, and then G is fixed, which means the Zariski closure is simply diagonal embedding of PSL2C into this product of the conjugation. So it's not Zariski dense. Okay? And then since I was assuming each component project actual Zariski density inside the PSL2C times PSL2C and PSL2C, the only non-Zariski dense subgroup has to be just diagonal embedding of PSL2C into the product. So we have this equivalent statement. My representation is trivial if and only if the corresponding self-joining group is not Zariski dense. Okay? So the rigidity question, we can reformulate in the way. Try to understand obstructions to the Zariski density of the self-joining group. Okay? So for given representation, when is this self-joining group not Zariski dense? So here's in this point of view, most of rigidity theorem can be reformulated in the following way. If gamma is a lattice, you give me any discrete basic representation, and I form self-joining group, and this self-joining cannot be Zariski dense in the product of PSL2C times PSL2C. Okay. See, like when you give me some group, of course, it's not easy to decide whether it's Zariski dense or not Zariski dense. So this is why Mostow had to prove by going to infinity and then using all this algebraicity to prove the self-joining group cannot be Zariski dense. Of course, he didn't prove directly this group is not Zariski dense, but that's what he proved. Okay, so in our setting, so now our goal is that if my boundary maps too many circular slices of limit set to circles, then we want to show this corresponding self-joining group cannot be Zariski dense. Okay, so now how do you show this self-joining group cannot be Zariski dense? Again, we go to infinity to prove a rigidity statement. Okay. So here I have a product H3 times H3. The geometric boundary is large. The geometric boundary consists of H3 times the boundary of H3, S2, union S2 times H3, union S2 times S2. So geometric boundary is large, but we don't look at that. We're not looking at the geometric boundary. We'll be looking at only S2 times S2. It's called the first-Hamburg boundary in this case. And then the limit set of my self-joining group is defined in the same way. So I take a base point to say O, O, okay? And then we look at the orbit of my self-joining group here, okay? So it is important my group is a graph group. So it is possible it will accumulate in one component, but it may not accumulate in the second component, okay? Then we don't take this point. We discard those points. We only collect those points which accumulate simultaneously, and then that is our limit set here. Okay? And it turns out this limit set is the graph of my first limit set, the limit set of my gamma via the boundary map. So my limit set here consists of Cushy, F Cushy, and the F was my boundary map. Okay? So it's important again. Of course, this is contained in the product of my limit set of the first group times the limit set of my second group, but it's not all of them. It is some graph sitting in this product. So now I have my gamma row in the product of PSL2C, PSL2C, and we look at its action on the space of tori intersecting the limit set. So by torus, I mean the pair of circles. I have a pair of circles, C1, C2, and my condition is that this C1, C2, I have two subsets in S2 times S2, and then we ask this torus to intersect my limit set of the self-joining group. Okay? Because gamma rho, so each component preserves the circles. So, and then of course gamma rho preserves this limit set. So the gamma rho will preserve this space, the space of tori intersecting the limit set. So we look at this section. So first, if omega is disconnected, or if omega is at least two connected components, and we show that if F maps some circular slice, say C1 intersection lambda to C2, another circle, then when you look at the orbit of this C1, C2 under our self-joining group, its closure cannot be everything. It cannot be dense. Okay? So this is where this condition about disconnectedness actually is important. So here's the example here to illustrate this point. So how do I use actually there is at least two connected components here. So I have two connected components, so I have two green dots. Okay, one dot from each connected component, and then I'm taking third point which is in the limit set. Okay, and then I draw this circle. And then on the other side here, I'm going to draw a circle. So if this point is Cushy, then I will have F Cushy because F is my boundary map. And then here I draw this circle which maps, which contains this F Cushy, but which intersect my limit set only at one point. And then we show that actually this kind of torus, this is a torus inside my set because this torus intersect contains Cushy, F Cushy, which is my limit point. But this torus cannot be approximated by C1, C2 if F maps C1 intersection lambda to C2. The reason is that if I have a sequence, say, gamma IC1 converging to this D1, then because of this, this property that actually this limiting circle contains 2 points from different connected components, we can show that on the other side, the limiting circle must contain at least 2 limit points as well. But here, I gave you this circle which intersected the limit points only 1 point. So you can actually, you can construct explicit tori which cannot be approximated in this way. On the other hand, so see, we want to show gamma rho cannot be Zariski dense if it maps too many circular slices to circular slices to circles. So step 2 of our proof is that, on the other hand, if my self-joining group was Zariski dense, then there are lots of tori with dense gamma orbi, with dense gamma rho orbi. Okay? So for instance, there has to be lots of tori whose closure must contain this explicit torus D1, D2. So it is this step 2 which uses dynamics of one parameter diagonal subgroup on this quotient homogeneous space PSL2C times PSL2C modulo gamma rho. So Mostow uses these dynamics of Kleinian groups, more precisely ergodicity of geodesic flow, to prove there is no cage conformal deformation. So for us, it is this step 2 part that where we use dynamics. But we don't use dynamics of Kleinian group, but we use dynamics of diagonal group on the higher rank homogeneous space of infinite volume. Okay? I also want to say that even if you started with a lattice gamma, gamma rho is never a lattice. So this space is always infinite volume. Okay? So maybe a little bit more details. So here I have a PSL2C times PSL2C. So I have a 2-dimensional diagonal group. So its Cartan subspace can be identified with a plane. Okay? So by taking the log of these diagonals, I have a plane, which is my Cartan space. And here, what is called the limit cone plays a very important role. So what is the limit cone? So formally, it is defined to be asymptotic cone of the Cartan projection of my discrete group gamma inside my algebraic group. But in this specific case, so my Cartan projection is simply this. I look at the pair of displacement functions here. Okay, so I just fix fixed base point O, O, and then consider this distance is a hyperbolic distance of gamma O to O, and then hyperbolic distance of rho gamma O to O. Okay, so in this picture, I have this countably many points. Okay? This is my Cartan projection of gamma, and by asymptotic cone, we simply mean we collect all the limiting directions. Okay? So for instance, these points here, they don't accumulate. So here, the outside, it doesn't accumulate. So we discard these points. So you collect all the limiting directions of the Cartan projection of gamma, and then that is what's called the limit cone. And it is a theorem by Benoit. He showed that this limit cone is always a convex cone. It's not obvious because I just collected the limiting directions. Why does it have to be a convex cone? But he proved it's a convex cone. And moreover, he proved Zariski density of gamma rho implies that the interior of this limit cone should be non-empty. Okay? So just like in my picture, I draw this picture. It's a convex cone with a non-empty interior. So the limit cone for my Zariski dense self-joining must look like this. So, I denoted by A. So this is the 2-dimensional diagonal group inside PSL2C times PSL2C. And this PSL2C times PSL2C mode gamma rho. So this is a huge space, and then many of A orbits will be divergent, and then they are not, they are trivial dynamically. So we don't want to consider them. And we only collect those non-divergent A orbits, and then that is a non-wandering set for A action. And we denote by omega gamma. So you should imagine omega gamma is a highly non-homogeneous space. It's a fractal space. Okay, so it kind of it's a union of A orbits which connects these limit points. Okay? So it was shown by Deng in 2020 in this specific case, but more generally by Chao Sakar. They are my students. It was part of their thesis. So what they showed is that if gamma rho is a Zariski dense, then we know that by Benoit theorem, the limicon has a non-empty interior. And what they showed is that for any direction in the interior of the limicon, you look at the one parameter diagonal flow in that direction, and this action is topologically mixing on omega gamma. Okay? So I have this limicon here, and then take any direction in the interior. Okay? And then any direction gives me, by taking an exponential map, it gives me one parameter diagonal group. So I have a huge space, so one parameter diagonal group to act in a topologically mixing way is highly non-trivial statement. So, but the statement is that it is topologically mixing. I think we've heard of the word mixing from maybe Paul Nelson's talk, but here topologically mixing means, so take any open subset intersecting omega gamma, and then you look at the orbit under this one parameter diagonal group, and then this orbit has to intersect every other open set. That's what topologically mixing means. Okay? So this topologically mixing, we use this information to say that there exists a dense semi-orbit, AU plus orbit. AU plus means that we're only looking at the R plus action, not the R minus action. So there exists a dense AU orbit, and using this information, we proved that in the limit set, we had this limit set. Inside of this limit set, there exists a dense subset such that for every tori, for every torus intersecting this dense subset, the orbit, gamma rho orbit of that torus and its closure contains all the tori intersecting limit set at least 2 points. Okay. But then now if you have the union, I mean the set of all the tori intersecting the limit set at least 2 points, of course it's not obvious actually why it will be our entire space. And then in this step, we use the theorem of Prasad and Rapinchu, and also theorem of Kibalchi and Roji. Okay? So this is how we get a contradiction. Okay? So under the condition, omega is disconnected, we said that you cannot have too many dense tori orbit, but then if gamma is Zariski dense, you have lots of dense tori orbit. So this is a contradiction we obtain.
Say that a bit more slowly.
Sorry, okay. Yeah. In this case, so you, right, so it's a statement about actually R proximal element. So in this specific case, SL2C times SL2C, if you have a Zariski dense group, it means that it contains a loxodromic element. So, and then, right, and then, but then its angular component actually will capture all of SO2 times SO2. Yeah, so that's what it is. Right. So now we have actually stronger measure-theoretic version. In the case gamma and rho gamma are both convex or compact. So now I have to speak very slowly because Peter asked me to do. So gamma and rho gamma. So I defined what is geometrically finite, and then I drew also some picture of cusps, and then convex cocompact means it's geometry finite, but then no cusps. Okay, that's what convex cocompact means. And if gamma and then rho gamma convex cocompact, and then again we assume omega is disconnected. And then in this case, so we collect all the circular slices, C intersection lambda, which are mapped to circles by my boundary map F. Okay? So I have my limit set of a convex compact Kleinian group, and then here I'm going to look at the union of all the circular slices which are mapped to circles by my boundary map. So I get some subset of my limit set, right? I get some subset of my limit set, and the theorem is that either this set is everything, or it's a measure theoretically trivial. It's empty. So H of delta here denotes the delta dimensional Hausdorff measure, and what's the relevance here? So if you have a convex or compact Kleinian group, So you can imagine here is one example of the limit set of a convex or compact Kleinian group. And it is a classical theorem of Sullivan. You look at the Hausdorff measure. Okay? So the relevant Hausdorff measure is exactly the Hausdorff measure of dimension given by the Hausdorff dimension of the limit set. Okay, here. And then Sullivan showed when gamma is convex or compact, this Hausdorff measure is non-trivial on the limit set, meaning that it is finite and also it is positive. So this is actually unique non-trivial measure on your limit set. Okay? So our theorem says that either limit set is everything or this delta dimensional Hausdorff measure of this union of circular slices has measure 0 when delta is the Hausdorff dimension of the limit set. In particular, combined with our previous theorem, it says that as soon as Hausdorff measure is of this set is positive, then your representation is trivial. So we formulated our theorem in this way because as was motivated by Alphonse measure conjecture theorem. It's either everything or it's a measure theoretically trivial. So this is the statement. And for this theorem, now we need much stronger than what is called topological mixing, but we used now ergodicity of the one-dimensional diagonal flow. So I have a same homogeneous space, PSL2C times PSL2C, modulo my self-joining group. And so I proved this with joint work with Berger, Landersberg, and Minjuli, 2021. What you prove is that suppose gamma and rho gamma are both convex or compact, and then suppose my self-joining group is Zariski dense, and then as before, for any direction in this interior of the limit cone, we look at this one-parameter diagonal group. And then the statement is that this one-parameter diagonal group acts ergodically, okay, with respect to a Bowen-Margulis-Sullivan measure corresponding to this direction. Okay? So it turns out actually for every direction, there is a unique correct measure. Okay? So when you change the direction, this measure changes. This is why we have this subscript U for the BMS. So BMS is a short for Bowen-Margulis-Sullivan measure. So this is a higher rank Bowen-Margulis-Sullivan measure. For every direction, I have a Bowen-Margulis-Sullivan measure in that direction. And then this directional flow is ergodic. That's the statement. And I want to point out, oh, by the way, maybe I might have to define what ergodic means. So ergodic means any invariant subset is in measure sense is trivial. Either measure 0 or complement is measure 0. Okay? So that's what ergodic means. And I want to say ergodicity is much more subtle question when you deal with the infinite measure. Okay? So even though here gamma and rho gamma are convex or compact, the higher rank BMS measure for this self-joining group is always infinite measure. Okay? So when you have an infinite measure, it is much subtle to decide whether your dynamical system is ergodic or not. But that's what they proved. But the key point, so what is it about gamma and rho gamma convex or compact? The reason is that in this case, the self-joining group becomes something called the Anasov subgroup of PSL2C times PSL2C. And then my ambient group has rank 2, which is less than 3. So this theorem with Berger, Landersberg, Lee is much more general. Whenever I have a Zariski dense Anasov subgroup over higher rank real semisimple algebraic group, and the directional flow coming from the interior of the limit cone is ergodic if and only if the rank has to be n most 3. Okay? So if the rank is higher than 3, then it is not ergodic. But a self-joining group has rank 2. Okay? So what is Anasov group? So I don't have time to go into this, but Anasov group is considered to be higher rank version of convex or compact group. And then I can prepare a whole new talk on Anasov group, Peter, next time. Okay. So now what's the relevance of our theorem with this Bowen-Margulis-Sullivan measure? The point is that, so when I have a delta dimensional Hausdorff measure, so in general, so I have this Furstenberg boundary, and this there is also notion of a higher rank Peterson-Sullivan measure on this Furstenberg boundary. But these higher rank Peterson-Sullivan measures are much more mysterious than the rank 1 case. Okay? So there is a classification parameterized by something, but it is much less explicit. It is much higher to understand, much more non-trivial to understand what are the higher rank Peter-Sullivan measures. But in our case, so I have this Hausdorff measure, and then I can push forward this Hausdorff measure to my Furstenberg boundary using identity times my boundary map, and then we prove that actually this indeed is a higher rank Peter-Sullivan measure on our Furstenberg boundary. And moreover, using the classification of Peter-Sullivan measures done jointly with my former student Lee, we can prove actually this higher rank Peter-Sullivan measure does correspond to Bowen-Margulis-Sullivan measure for the interior direction. Okay, this is important. And then, so these 2 points, the points which connects this Rigidity theorem with our measure-theoretical version about this rigidity theorem. Okay, I have maybe 1 minute. So this is my last slide, actually second last slide. So there's something called the Sullivan's dictionary, and this Sullivan's dictionary is a dictionary about Kleinian groups and their rational maps. So when you prove this theorem about Kleinian groups, it was very natural for us to ask if there is an analog for rational maps. Okay, so if you're not familiar with the rational maps, okay, it's just say quadratic polynomial, z squared plus c. So you can just think of this quadratic polynomial. So suppose we have 2 rational maps of degree n least to 2. Okay, and then the Julia set is what is called what corresponds to the limit set, and we assume the Julia set is not contained in any circle. So this corresponds to the condition that the Kleinian group is not Zariski dense. Okay? And then we assume the Fatu set, which is the complement of Julia set, is not connected. And suppose I have 2 rational maps, and suppose they are quasi-conformally conjugate. Okay? So suppose H2 is conjugate to H1 by some quasi-conformal homeomorphism F. And if this quasi-conformal homeomorphism maps all the circles in the Julia set to circles, is F conformal, is F Möbius transformation. And if this H1, H2 rational maps are hyperbolic rational maps, they correspond to convex or compact Kleinian groups, and is there also a measure-theoretical version of this statement? So this was a question, and congratulations, Peter. Yeah.
What is that? Where's that coming from?
So this Anasov group, so of course this, if you look at this non-wandering set, which is kind of fractal subset inside this space, and this Anasov group has a feature that this is a vector bundle over some compact homogeneous space. Okay? And then this vector bundle has fiber, which is R to the rank -1. Okay, so in my self-joining case, it will be just a line bundle, but then if you have rank K, then it will be a vector bundle with fiber R to the K -1. Okay, now you think about this analogy with the random walks. You know this drunken person comes back to home, but drunken birds actually goes away, right? So if this fiber bundle has fiber either R or R2, then you have recurrence. But if it's bigger than 3, then it goes away. So this is where the dichotomy happens. Yep.
Mostow's rigidity theorem, higher dimensions, do any of these results?
Thank you. So I have a confession. I bribed Simeon for this question before my lecture. So, right, exactly. Most of rigidity theorem holds for higher dimension. So we prove actually all of our theorem in higher dimension too. So in the higher dimension case, you have exactly the same setup. So the strongest thing you could ask is that what if circular slices go some proper spheres, right? This, and then our theorem is proved in that generality. Yeah. Thank you, Simeon.
So let me ask you another question, since you brought up higher rank. In this thin group, so there are proofs that use harmonic maps of super rigidity and higher rank. What, have you ever thought about trying to understand some of those things for thin groups?
In higher rank.
In higher rank.
Right.
After Corlett, what I have in mind. In other words, not Margulis,
Right, so I have a recent paper with the Canary and then Andy Zimmer about rigidity for higher rank discrete subgroups, but for non-lattices. So you can ask like various generalizations of these things, right? But then a huge difference between real hyperbolic, even actually you don't have to go to the higher rank, but you can go to say, for instance, a complex hyperbolic space. You can ask the same question. But in the complex hyperbolic space case, for instance, there are two different kind of circles. There are something called the real circles and then complex circles. And then we try to think a little bit about like, what if it maps all the real circles to real circles? I mean, the circular slices. Is it true that F is algebraic? But then somehow the Kleinian group in complex hyperbolic group is much less understood. There are much less picture, okay? And then now you go to higher rank, so what is circle? Because the higher rank or also the complex hyperbolic group, the big difference is that the action of the isometry on the boundary is not conformal. So it's not conformal. So then what is the right question? So one theorem I recently proved is that if your limit map is a bi-Lipschitz, okay, you still have this boundary map from the limit set to limit set, and then if you impose the condition, it is locally bi-Lipschitz, then we can prove actually you have theorems like Margulis, like it has to extend to the ambient group. Yeah, so we have this proof.
You know, if you take a lattice gamma, non-compact, and if you take rho in your setup isomorphic, then rho gamma is a lattice is what you are assuming.
No, I'm not assuming.
Because, you know, you applied Mostow's theorem for product and so on.
For cocompact, I think it is the cohomological region that actually yes, yeah.
Not cocompact.
Right.
So for example, for SL2R,
Uh-huh.
the statement fails because free group
I see. Okay,
can
okay.
be made into
Okay.
thin.
Yes, okay. So what Gopal is saying that, okay, for most of cocompact, for most of the rigidity theorem for cocompact groups, so my statement was correct as it is, but then when I stated for non-cocompact finite volume case, I should have assumed that my image is also lattice, okay? But for cocompact, it is automatic because of the cohomological dimension region, but for non-uniform lattice, that condition has to be assumed.
I have proved that.
Oh, you proved? Okay. So the statement is as true.
Some 50 years ago, you know, when I used to work on discrete subgroup,
Okay.
so it's true that an isomorphism
Lattice to lattice, I see.
except for SL2R.
Okay, okay, thank you.
To wait long enough, the corrected version. Other questions, comments?